Well, as we come down the home stretch here, we got just a couple of topics left, and I picked out a topic tonight that's, I think, fairly innocent, but it's been tripping us up, and it's kind of been a trend on our last few Grizzlies. So we're going to talk about angles in their most basic form, converting them back and forth from radians to degrees, getting more comfortable in that state, and then also extend it to the unit circle. So just right off the bat here, we're going to talk about how to convert from degrees to radians. What's going to happen is they're going to give you an angle ahead of time, and we're going to just simply multiply it by pi over 180. So essentially, as that happens, you get your theta in degrees, and it's pi over 180, and you just reduce it. So for this first one here, you take the 90, it's technically over 1, we multiply by, pi over 180, and as you reduce that, of course, 90 goes into 180 twice, so we get pi over 2. And that's one that we've memorized quite well. In fact, we've memorized a few of these. Hopefully you've memorized that 30 degrees is equivalent to pi over 6. Hopefully you've memorized that 60 degrees is pi over 3. Notice how the 3's and the 6's flip-flop. And then 45 degrees, another famous one, is pi over 4. And if you've memorized those three, we could really cheat on some of these other ones. For instance, when you take a look at 120, if you don't feel like multiplying by pi over 180, not that that's that hard, but what you'll notice is it's twice as big as 60. So what I'm going to do is I'm going to take the radian for 60 and just double it, and that's going to give me 2 pi over 3. Another one that you'll notice here is 45 is a reference angle for 225. In fact, 45 goes into 225 5 times. So I'm going to multiply this angle by 5. And we've got 5 pi over 4, so you can cheat on some of those famous recognizable ones. But if that doesn't, if you don't feel 100% comfortable, just keep it simple. Multiply by pi over 180. Again, real quick, they're going to give you an angle. It's going to be in radians this time. And to convert it to degrees, we're going to multiply by 180 over pi and see where that takes you. But what I'm going to do is I'm going to rely on the fact that I've memorized some of the basic ones, and we're going to talk to you about how to cheat just a little bit here. As soon as you see the pi over 6, you're thinking 30 degrees, and then we just got to multiply it by the 5 that was sitting out front. 5 times 30 is 150 degrees. Let's see, pi over 2 is 90. If I triple that, I get 270 degrees. And over here, pi over 4 is 45 degrees, and again, if I triple that, I'll get, 135 degrees. Again, we could have... So I didn't necessarily use this technique. I could have used that technique on any three of these. I could have multiplied by 180 over pi. One of the things you'll notice is that the pi's do cancel, and then you just do 3 times 180, and then divide by 4. Now this is the slide in particular that's been nipping us in the butt on these Grizzlies we've seen. Now it says we should all feel comfortable with the fact that radians are not always in terms of pi. Usually they are, typically they are, but not every time. There's no rule that says they have to be. And so what happens is they may give you an angle like this one. It's in radians, but it's not in terms of pi. Here's what we're doing. Everybody seems to be like sprinkling in their own pi. They just rewrite it as 5.8 pi. I'll tell you what, 5.8 times 3.14 is a lot different than just plain old 5.8. So what we have to do, we have to be disciplined. Leave it as 5.8, and then just multiply by 180 over pi. What we're going to do now is we're going to pick up our calculator. We're going to type in 5.8 times 180, hit enter, divide that by pi, see what we get. My calculator says 332.3155 yada 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 degrees. They said rounded to the nearest tenth of a degree here, and nearest degree. I can't read, so I'm going to just say 332 degrees. All right. Now what I need you guys to do is I need you to tackle Part B and Part C on your own in your notebook, and that'll be something we're looking for specifically tomorrow when we check your notebook. The unit circle here, as we switch gears and kind of move on to our second topic tonight, is something that I really want to simplify for you and help you understand how easy it really can be. The unit circle is a very basic circle in its simplest form. It's centered at the origin and happens to have a radius of 1 unit. It doesn't get any better than that. So just a nice warm-up question here. Which of the following equations represents the unit circle? I don't like number 1. Nothing is squared. It's linear. I don't like number 2. The x is getting squared, therefore it's a parabola. I don't like number 4 because that one's centered at the point 1, 1. But I do like number 3. It's centered at the origin with a radius of 1. It's good to go. And there's a lot of nonsense with the unit circle, a lot of good things. But here's the one thing you gotta know. They're going to give you an ordered pair that falls on the edge of the unit circle. And what you need to know is that the x-coordinate is equivalent to the cosine of angle theta, and that the y-coordinate is equivalent to the sine of angle theta. And just remember that it does go in alphabetical order. For instance, X comes before Y in the alphabet, and C comes before S in the alphabet, and so it's very alphabetical. So here's what's happening. Here's the unit circle that includes all of the common popular points. When you sit down to take your Regents exam, they're going to expect that you're comfortable with this circle and that you can go around that circle and nail each of these points in their ordered pairs. And so I'm going to go real slow on the first couple, then we'll whip through the rest of them because it's very much the same. So I want you to visualize this circle right here. I'm sorry, this right triangle. Angle theta is always the corner of the triangle that's closest to the origin. And what's going to happen here is we're trying to get that ordered pair up here at 30 degrees. The x-coordinate is simply going to be the cosine of 30 degrees, which is radical 3 over 2. And then the y-coordinate is going to be the sine of 30 degrees, which is 1/2. Okay, so those are two exact values that we've memorized from our table, and that helped us identify that ordered pair. As we progress counterclockwise, visualize this red right triangle now. Obviously the angle got a little bigger. The angle is again closest to the origin. The cosine of 45 degrees is radical 2 over 2, and the sine is also radical 2 over 2. Let's see, let's go up here, and I'm going to grab a new color here. Let's grab some green. So we're talking about this triangle right here. And let's see here, angle's still closest to the origin. The cosine of 60 degrees is 1/2, and the sine of 60 degrees is radical 3 over 2. And that does it for the first quadrant. But what's going to happen as we progress through the other quadrants, it pretty much stays the same. So for instance, when I get to 120, can you also visualize this triangle here? Does this green triangle look congruent to the first green triangle I drew? I hope you're thinking yes. And the angle here is again has a measure of 60 degrees. The other side, here's your 120 here, but then your reference angle is 60 again. And so what's happening is we're getting the same ordered pair we got at 60. The only difference is the x-coordinates negated. So as we go around this unit circle, the only thing that's really going to change are the signs. Visualize this rascal right here at 240. Now we've got negative 1/2 and a negative radical 3 over 2. Visualize this rascal here. Notice we're kind of, the four green triangles are making a gigantic bow tie. So 300 degrees, we're going to have a positive 1/2, but a negative radical 3 over 2 because sine is negative in the fourth. One last comment here before we dismiss the unit circle. There's four special points, 0 degrees, 90 degrees, 180, 270, and then back here actually we'll call a fifth point at 360 degrees. Those don't fall within a quadrant, okay? Those are what divide the quadrants up. Those are called quadrantal angles, and they're very special. And so at 90 degrees here, because the length of the radius of our circle here, it has a length of 1, we're going to say that's just 0, 1. This is negative 1, 0 back here. Of course, this is 0, negative 1. And of course, over here is 1, 0. So those are your four quadrantal angles that don't fall within quadrants. As we buzz through these next three examples, I want you to be very visual here. I'm going to try to sketch these out for you the best I can. We've got ourselves a generic unit circle here. 150 takes you almost all the way to 180. So right there is what 150 looks like. Of course, his reference angle is 30 degrees. So 30 degrees, I'm going to say, let's see, I need cosine of 30, and then I need the sine of 30. And boy, don't get it easier than that, does it? Radical 3 over 2, 1/2. So that's the point that corresponds to 30. Now how about the 150? All that's going to change is we're going to negate the x-coordinate because cosine's negative in the second, but the y-coordinate stays the same. So that one's good to go. Again, let's try to sketch 225 really quick. 225 would probably split that third quadrant right in half. So here's 225, and of course his reference angle is that little gap right there, 45 degrees. And I need the cosine of 45, and let's see. Actually, let's just do 45 right now, so it is positive on both of these. And then when we start talking about 225 degrees, because we're in the third quadrant, both cosine's going to be negative and sine's going to be negative. So those are the two respective ordered pairs that they asked for. And then last but not least, 300 lives over here in the fourth quadrant, just a whisker past 270. Got your big 300 there, then your reference angle is the sliver on the other side in there. So let's see, 360 minus 300 is 60 degrees reference angle. Cosine of 60 is 1/2, and the sine of 60 is radical 3 over 2. And if I start worrying about 300 degrees, now what's going to happen is my cosine value is still positive in the fourth quadrant, but we're going to negate the sine value. So that's the ordered pair we get there. Our very last slide they're giving us three ordered pairs that lie perfectly on the edge of the unit circle, and they want us to identify the angle that corresponds to those points. And so, again, I want to be very visual here. The first one, we've got our unit circle, and -1, 0 is right there. What is that angle? Of course, it's 180 degrees, or you could say it's pi radians. Either of those answers would be perfectly acceptable in my book. This next one, we're kind of going to eyeball it. We're in the first quadrant because both of those points are positive. So, maybe, let's see, maybe we're right about there. What you know is that the cosine of this mysterious angle is equal to 1/2, and therefore theta must be 60 degrees. You could have taken this approach. You could have said that the sine of theta, or this mysterious angle, was equal to radical 3 over 2, and then if you took the inverse sine of both sides, you'd also end up with another angle. You'd also get 60 again, just to confirm your first answer. Last but not least, we've got, let's see, positive x and a negative y value. So that's going to throw me down here in the fourth quadrant. We've got to try to identify that angle right there. And so I'm thinking that the cosine of theta is equal to radical 2 over 2. And the first thing that came to mind was 45 degrees. But of course, we know that 45 can't be the final answer because I'm looking for a fourth quadrant. So I'm going to say, all right, let's do 360 minus that reference angle for a final answer of 315 degrees. Boom, there it is. Hope you enjoyed. We'll see you tomorrow.